Hello. Hello. Hi, welcome all to our 23rd episode of Tech Container. So, Tech Container is a platform from Polaris where we discuss our latest trends in the tech world. Today, we have our in-house data scientist, Vital Vialas. He's from the Valencia team, and he's been with Polaris for 1 year. He has a total experience of 5 years before Polaris, and he also has a PhD in bioinformatics. Today, he'll enlighten us on the time series of forecasting. So, any data set that contains history records like stock market, medical records, or climate will all be subject to this forecasting analysis. So, I'll pass it on to Vital for his presentation. Thank you.
Thank you for the introduction. Am I audible? Can you all hear me well? Just nod your heads or something. Thank you.
Yes.
Just start sharing my screen. Yeah, I will be talking about time series analysis and forecasting within the field, within Python specifically. So I hope everybody is at least a little bit familiar with the topic. And if you're not, I hope you find it interesting. This is an outline of the things I want to talk about today. As you can see, it's quite a long list, so it's quite exhaustive. I hope I will be covering all of it, but I'm realizing it might be a bit too ambitious for a talk of 1 hour. So I won't be talking about each of the models in very much detail, but hopefully you will get a nice overview of all these methods, starting from some general concepts. And then I will be talking about univariate and multivariate models and supervised models, and then some more advanced models. And please stop me anytime if anyone has any questions, although I think there's some dedicated Q&A period in the end of the session. Well, univariate models, as you can imagine, are models that use only one variable. So it uses only the past values and no other extra variables. So you can see here a very simple pandas data frame where it shows the price over time of ice cream sales. And there's a nice regularity here where we see the price goes up in the summer. And it's just a simple example. The target variable is what we want to predict. If we wanted to use this particular data set, it would be the price, right? And then there are supervised models, which are the models that use extra variables that are related to the target variable. In this particular example here, imagine we want to see the trend over time of subscribers of followers or any kind of subscribers to any service. And then we have two extra columns in the data frame, the inversion in marketing or advertisements, and then promotion. And then the time points are in quarters. And what you can see here is that the trend of the subscribers is very similar to the trends of the other two explanatory variables. This would be a simple example of a supervised model with the explanatory variables. One important concept in statistics in general is the correlation coefficient, which measures how much two variables are correlated with each other. There's a simple pandas method that is core and will create a matrix like this, where the correlation coefficient of one variable with itself, it's always 1. But we can see from the previous example that these correlation coefficients are very high, as we saw in the previous plot. It can also go to negative values, so this coefficient goes from -1 to 1. I'm talking in very basic terms because I don't really know the profiles in the audience. For some of you, this will be very simple, but I hope someone will find it new. And then for evaluating how good our predictions are, imagine we have a time series like this where we have the real values in blue and the predictions in orange. So we want to compare how good is our prediction compared to the real, relative to the real values. For that, we have a set of error metrics where we have the actual value, the predicted value, and we can estimate how good is the forecast compared to the actual values. And one simple metric for that is MSE, or the mean squared error, which basically takes the sum of the squared difference and divides by the total number of records. Or in other words, it's the average of the squared differences between the prediction values and actual values. And then you get a score like this in this particular case. So this is quite commonplace, but even more so is RMSE, which is the root, the rooted mean squared error, which is basically taking the square root of the previous MSE metric. In this case, it is easier to interpret because by taking the square root, we scale back the error to the original unit of the values. So imagine the actual values are centimeters, RMSE would be 7 centimeters as well. So it's easier to interpret. It's an error of 7 centimeters, and then you can figure out if it's good enough for you or not, depending on the standard deviation of the actual values. And then commonplace in all machine learning methods is this approach for evaluating how good or bad a model is. So it consists of splitting the data set into one part, which is usually the longest part, will be used for training the model, and then the test is the part that is used for evaluating the model. In time series in particular, we have to consider that the data is sequential normally, or in other use cases or applications, it doesn't matter where in the data set we put the test, right? And sometimes, if you're familiar with this method from the scikit-learn library, shuffle is set to true, but in this particular case, or in the case of time series, it's important to set it to false. So the test part will be the last part in the data set. In addition to this, so we only use one simple train and test split, we risk overfitting. Overfitting means the predictions are too specific to the data set that was fitted for the model. It could get a very good error metric, but it might not be able to generate good predictions. So it's too specifically tailored for the data set, and it's not generalizable. That means the model is overfit. So to prevent overfitting in time series, what we can do is cross-validation, which means repeating the train and test split over different periods of the data set. Always the train part has to be previous to the test part, because we know it's sequential data, so it's important to keep the sequential order. Then we would have an error for each of the splits, and then we take the average error, and that way we get a cross-validation error that tests or evaluates the model over a larger proportion of the data set. This is a sample here where each of these dashed lines, the period between the dashed lines, represent one of the splits in the cross-fault validation. And the light green line is the prediction. And you see in some of the splits, the predictions are a bit more accurate, and in some others are worse. But overall, we will evaluate the model over a longer period. This is mostly to prevent overfitting and to know our predictions will be generalizable for unseen or out of sample data. Now moving on to univariate models, ARIMA, which you might have heard of, is sometimes referred to as a model itself, but it's actually built of several building blocks or sub models which work on their own as well, and these are the parts of it. The parameters or the parameters that control each of these parts are usually referred as P, D, and Q for the autoregression, integration, and moving average parts. And I will show some examples of all of these. But what's important to know is that these are the building blocks for many of the time series models. And I'm showing here some example of autoregression. It is an example of forecasting the daily temperature, daily minimum temperature. For autoregression, what's important is to know the autocorrelation of a variable, which means how a variable correlates with itself. Or in other words, knowing that the past values influence the future. In time series, a positive correlation means a higher value in the current time point will mean even higher value in the following time point. An example of this would be, for example, the stock market. When a stock goes high, people want to buy more of that stock, which means even it will go even higher. Negative means, well, the opposite. A higher value in one time point will mean a lower value in the following. So how can we see the correlation of in a univariate data set, knowing that correlation is a pairwise metric, as we saw in the matrix before? Well, what we can do is simply applying a shift of one or more lags. This is very simple to achieve. There's a very convenient function in pandas, which is called lag plot, which will basically plot the value of the variable along with the value for the following time point. Then we see in this particular case as well, the correlation is quite clear, quite high value of the time with the following time point. Two more important concepts here are stationarity and differencing. Stationarity means that some of these models need the data to be stationary, meaning the data should not have a long-term trend, like going up or down over a long period of time. So what we can do to remove the stationarity is differencing. Basically, rather than modeling the original values in the dataset, we can take the differences between each value and the previous or the following for any number of lags. In this case here, I can't remember because I didn't put the label of the axis. I'm not exactly sure what this model is showing, but what's interesting here is the autoregression model can be imported directly from the stats models library. And in this particular case, it's using 29 whatever the time unit is, 29 time points as lags. Then the following component of the ARIMA family of models is the moving average. Rather than looking at the past values of the data set, it looks at the error that the model created in the past time points. So the error would be this component here, and then there's a coefficient that multiplies the error for each of the Q values. Remember, Q is the order of the MA model, or the parameter that controls how many of these steps are. Then one may wonder, how can we if we don't have the model yet, how can we see the error in the past? Well, that's achieved by an algorithm called nonlinear least squares, which basically iterates over different values for the coefficients and then solves the equation. And that way, by iterating, we can identify the model that produces the lowest error. This example here shows how differencing works. You see the trend here is clearly going up in stock price over time, but by taking the difference, just subtracting the previous value from the current value, we can get a graph that has a median or a mean around 0. This shows the ARIMA library, which is part of the stats models library again, how it's implemented here. And you see the parameters are usually P, D, and Q for the auto regression, for the differencing, and for the moving average. In this particular case, we are doing working forward prediction. So for every point we predict, we can append that point to the training dataset for the following prediction. So that way we can sometimes increase the performance of the model. And then there's the combination of the two, autoregression plus moving average. The autoregression is this part of the model which multiplies coefficients by the past observations for a p order, and is the moving average part of the equation that looks at the past errors for a q number of times, plus an error plus a constant. And then the combination of all three parts, including the integration, would take those parameters P, I, sometimes called D, and Q, for each of the parts of the components of the model. This example here shows again the differencing when the original time series is transformed into a stationary dataset. And then sometimes you see SARIMA as well with an S in front. The S stands for seasonality. And this type of model is applied whenever we have a time series that we know has some seasonal effect, whether it's a thing of summer and winter and so on, or maybe it could be a seasonality that occurs every few years, like in this case. This case is a sample where the target variable is the weekly sales for different stores and containing different variables. This data set, as you see, is weekly data. That's why well, we import the SARIMA library again, and there's the order we explained earlier, and then there's additionally the equivalent for the seasonal aspect of the model. And in this case, it's 52 because it's weekly data, and then we are plotting, I think in this case it's years. I can't remember exactly, but yeah, when we using the seasonal ARIMA, we need 3 extra orders for the seasonal aspect of the component. And then I'm moving on to supervised models, starting off with the basic linear regression, which is basic high school math, but it's a good reference to always look at, where we have an independent variable and we want to predict a target variable. In this case, imagine predict the sales of hot chocolate based on the temperature. So we can just fit the line that best fits the data point based on least squares or some other method. And we can basically just get the equation that will predict the target variable by multiplying the coefficients and adding the intercept. Another very common spread supervised model is the decision tree, which you can think of as a long sequence of statements. In this particular case of the example here, imagine we want to predict the amount of rain. So then we have a number of splits for each data point we want to predict. In this case, if it's tropical or temperate, if it's rainy season or dry season, you could think of any number of splits based on different criteria. And as you can see, this can also fit non-linear data, which is very useful in some cases as well for time series. This is an example of how a decision tree would, or an example data set where we will apply a decision tree, where we have the target variable, which is the count of users that rent a public bicycle or rent a bicycle depending on different weather conditions. So this part here where it says feature engineering means adding extra variables to the original data set so we can use those during the training process. Yeah, so these are lags of the number of users, weather situation, can't remember exactly temperature and humidity. So then we create the train test split. Again, setting shuffle to false, so it's so we know it's going to be sequential, and then we just use the decision tree regressor from scikit-learn without any specific parameters, and we get a quite low R-squared value. So we may wonder how to improve this model. And this brings me to grid search. In the previous example, we used decision tree regressor with the default values for the parameters, but we know it has a few, and we initially don't have any idea what would be a good number for the minimum for the number of splits, right? So we can use grid search, and for each of the parameters, we provide a range of values where we think the optimal could be. So basically, grid search tries different combinations of all these parameters and will return the best set of parameters that provides the best result. And in this particular case, we see the R-squared value has improved by quite a margin. And if we plot the data, you can see it captures quite well. The orange is the actual data and blue is the prediction. Another very common supervised model is k-nearest neighbors, or KNN, which is very basic as well. But imagine we want to, the intuitive idea is just looking at the closest neighbors. So imagine we want to predict the height of a person based on the weight. We may look at, for instance, the 4 closest persons that have the most similar weight, and then we can just take the average height of those. It could also be a bit more elaborate. It could be a weighted average, but the basic idea behind it is that we can just look at the closest neighbors. In this example here, we may want to predict the traffic volume, imagine a number of vehicles going through a spot on the street. And it's also based on, or we also have other variables mostly related to the weather, but also the date and whether it's a holiday or not. So we can import the k-neighbors regressor from scikit-learn again, and we can do the train test split as usual. And we are only using these variables here, not the weather, just the date related variables. And we're using the model without any specific, with all the default parameters. We get a very good score. This is how it looks like. Again, the forecast in orange and the actual values in blue. And in this particular data set, KNN works very well for predicting traffic volume. And then decision trees leads me to the following type of supervised models, which is random forests. And as the name suggests, you can think of random forests as a collection of decision trees. And each of those decision trees would be slightly different. The idea behind this is that when one individual machine learning model performs not so great, a collection of multiple machine learning models, if we do the average prediction, it will be less likely to be wrong. That's the basic idea behind it. So the method of generating all those individual decision trees would be what we call bagging, which is the sum of bootstrapping and aggregation. Bootstrapping means getting a subset of the original training set with resampling. So meaning some of the data points could be repeated, but the difference, they would all be slightly different, the original data sets. And then we create a decision tree for each of those, which are sometimes called weak learners. And then each of those generates a prediction, then that is then aggregated using different methods, but basically an average. And here we're going to see an example of a random forest model where the data set is the number of sunspots on the surface of the sun over a very long time series. Again, we can do some feature engineering, so like enriching this data set with more data points, which are basically just lagged versions or lagged lag differences of the target variable. Again, as usual, we do the train and test split. We use all the variables that we created, and again we are using the random forest regressor with with the default parameters. And we see we can get quite good score. And then on the right side, what we see is using a grid search for getting the optimal values for n estimators and max features. N estimators is basically the number of decision trees that will be collected into the random forest. And we see the R² value is only very slightly better. So it's very much up to the user to decide when to use grid search. If the result with the default parameters is good enough, if we think we can improve it. And this is what it looks like in the plot. Again, fits the data very well. Another type of supervised model, again, XGBoost, similar to random forest, but in this case, there's a collection of decision trees as well. But how those decision trees are generated is by the method of boosting, which means the individual predictors are generated in an iterative way. So the most important features will be selected based on the weight to fit the following models. So the models that already explain quite a lot of the variance will not be given much weight for constructing the following tree. And this is XGBoost in action for predicting traffic volume again. We have the same dataset as before, and XGBoost regressor out of the box without any, with all the default parameters, gives a very good R-squared value. Yeah, I guess that was good enough. Then moving on to more advanced models, here you see the typical architecture of a neural network, where we have an input layer with as many nodes as variables in the dataset. Then we have a number of hidden layers with a number of nodes each. But those things, the number of hidden layers and the number of nodes in each of them are usual hyperparameters when creating a neural network model. And then output layer in a univariate type of model, there would only be one. And what you see on the right is the structure of a node or a cell, where we have a set of weights that are summed, and then the result is transformed by an activation function. There are different types of activation functions, but what this happens in each of the nodes, and by doing all this, we end up with a lot of parameters we need to calculate, right? All the weights, but this allows to fit almost any type of data, which is why neural networks are so popular and powerful too. And in particular, recurrent neural networks, the main difference or the addition they have to the compared to the other type of architecture, which is the one I showed before, that there's some feedback loop. So the output of one particular cell can be fed back into the cell. That's the main concept. And in particular, there's one type of RNN that is very used in time series, which is LSTM, which stands for long and short-term memory, which means it's good at capturing short-term variations, but also long-term. In this particular case, there are two weights coming into each cell, and each cell is also producing the weights for the following cell. And then there's a few complex activation functions that happen in the cell with some feedback loop. And this is what makes LSTM very suitable for sequential data, not only time series, but also text or maybe DNA sequences, that kind of thing. Anything that's sequential can benefit a lot from using LSTM. Here we are predicting, the target here is the temperature. It's a data set based on different atmospheric conditions, and we have a timestamp as well. So what's important when generating the data sets for training LSTM is that the data has to be in a particular format. So what this shows is that for a number of future and past steps, we create windowed data sets, which is what will be fed to the model. The train and test split is created as usual. And then in this particular case, it's an LSTM of eight hidden layers. the activation function for LSTM is usually this one here, and the input shape has to be in a particular format. And then, yeah, I forgot to mention about optimizers and backpropagation, but it's basically backpropagation is the method where the weights are calculated, and the algorithms or optimizers for doing the backpropagation are one of the most common, or in particular performing very well for LSTM, is Adam. Then we set the number of epochs, which is the number of times the backpropagation process will finish. It starts not considering all data at the same time, but uses the data in batches and moves backwards from the last layer to the first. So that's why it's called backpropagation. And then the way to evaluate neural networks is usually by looking at the loss function. The loss function would be equivalent more or less to the error matrix we saw. It means how far away we are in the predictions compared to the actual data. So there's a loss function for the train and for the test or validation in this case. And what we want to see is that the loss function drops very quickly in the initial epochs, which is what's more or less happening for the training data set here, but not so well for the validation. The steepest, the slope here, generally means the model is learning well. I forgot to mention also the learning rate. Learning rate is another hyperparameter for neural networks, which means how big is the step the optimizer takes when doing the backpropagation. So if the learning rate is very low, we might not find the optimum value, but if we might not have a big enough step to find the optimum. But if it's too high, we might step over it, and it's a balance, and there are different approaches to select a good value. And I think I'm reaching the end now. Prophet is another type of advanced, or it's one of the most recent models that has been developed for time series. It was open sourced by Facebook, and it's not really inventing any new approaches because it's based on some of the things we've seen before. But the advantage, I think, for Prophet is that it's very user-friendly. On the other hand, it's not as easy to tweak, but it performs very well in some cases, like we will see now. In this particular cases, visitors, can't remember exactly, but yeah, number of visitors that we are grouping by date here. So we have the sum of visitors in each of the consecutive dates. Prophet also requires this particular format. It expects timestamp column named exactly DS, and the target variable, it's just called Y. So it's agnostic of, or it's yeah, whatever variable is your target, it's going to be called Y for Prophet. And you see here the results of an out-of-the-box Prophet model, where we do the usual train and test split, and then Prophet also has some handy functions like for generating a future data frame and some more things for plotting as well. But you see here the predictions are matching quite well with a good R-squared value as well. And finally, I wanted to show this plot components function from model. So M here is the model object. And it's good to visualize what the different components the model is using. So in this particular case, the trend is going up, and then there's also weekly seasonality that goes down in the beginning of the week and then steadily goes up. This is another case, restaurant visitors. But yeah, we basically showing the same thing. There are different methods as well for adding different types of seasonality. If your data is daily, then you can specify a period and name the periodicity however you want, and then some more parameters to state how weak or strong that seasonality is. And we see here again the top two plots are the same as before, but then we have now monthly seasonality, where we see the beginning of the month is a bit lower and then goes up, and then you see the variation over the days of the month, the variation in how strong that component is. And this the final slide is just a touch of humor, a joke I make to my colleagues sometimes. And I'm done for now. Yeah.
Hi, thanks, Vital. We have few questions from the YouTube channel. I'll read them out. The first one's from Priya Ravi. She's asking, what is exponential smoothing in time series, and when is it used?
Yeah, exponential smoothing is another type of algorithm I didn't mention here, but I can't really tell when it should be applicable. It's just in some cases it's just a matter of choosing the model that performs better for your data set. And for that, we have seen different types of strategies for model evaluation. So exponential smoothing, I think it's also in scikit-learn. It would be just a matter of choosing it depending on I can't really tell for which type of data set is more suitable. I would just do some benchmark testing and use it accordingly.
Okay, and there's another question from Kaushik Ashok. What methods were used to deal with the null values in the data set? Were the methods used dependent on the model used for prediction?
Yeah, right. That's a good question, and I would say it depends mostly on how many null values. Sometimes, if it's just a few out of thousands, or you could just drop them and replace by the previous value, or you could do some KNN estimator, depending on how many variables you have. You could just do different types of fill methods, like replace the null value with an average or median, or you could do some more elaborate approach where you estimate the value of to replace the null value by using, for instance, KNN or some other approach.
Okay, do anyone of you here have any questions?
Vital, thanks for the presentation. I just have a basic question because we are like few of us are just starting into this in ML. So you were telling about algorithms, like are there any like derived upon algorithms like this industry or this domain will fit in for this, or it is kind of like what you were mentioning benchmark. So should we like try it out and then identify, or are there any standards that have been arrived so far in the industry that this can fit in for this industry? And that was my first question. Another one was like you were mentioning on the time series algorithm, time series models, right? Forecasting it. So there would be even when you go for weather forecasting, or you were telling about the share market, like stocks. So when you go for stocks, there might be a trend shift that might happen due to, say, any economic condition or any pandemics or something that might affect the values. So this external factor, can it be introduced into the training algorithms, or it is like kind of a linear or some pattern that has been like with the history we follow it? I just want to know that external factor can be introduced along with this so that the model can be even equipped with that. So that was my question.
Right. Regarding the first question about the applicability depending on the industry, all these types of models were, or some of these were created long back, and they have been applied successfully to very different types of data sets. And I think the algorithm itself is completely agnostic of the type of data. So my answer would be in that case, let's just do benchmarking and find whatever gives the best results. I think it's some people sometimes like to always try the latest method, LSTM or Prophet, where it's where some other models have not been tested yet, and it's not a matter of a preference or some algorithms being more suitable. It's just a matter of giving the best results. And regarding your second question, well, sometimes we can add exogenous variables or external variables into the models as long as they are predictable, so to speak. Sometimes, especially in the stock market, there are completely unforeseeable events that may produce very unexpected effects in the stock price. So yes and no. If it's recurrent or predictable, then we can add external variables. But all these methods will always suffer from completely unexpected events that cannot be modeled in any way.
Thanks, Vital. There are a few more questions.
Hello, Vital. Hi. A quick question. What are the developments since Prophet has come? Because Prophet has been few years. And what are the challenges, particularly with the time series data and prediction of it? And pertinent to her question, the previous question, if there are particular distributions from which the time series data is derived, okay, Poisson or exponential distribution, is that captured in this time series model?
Yeah, developments in Prophet. Yeah, I know it's been around for a few years. I know there's been some effort in combining or adding neural networks into the model somehow. It's called neural Prophet. I haven't tested it myself, but I've heard it's generating good results. The other question, I'm sorry, if you could remind me again.
Yeah, so if the time series data is derived from some underlying distribution, it will be typically it is not, it's very random, but if it is derived, then pertinent to a previous question she asked, whether that is captured in the time series prediction with any of these models.
Yeah, distributions that could fit time series data.
prior steps?
Yeah, I'm thinking depends on what the time series data looks like.
See,
As
simply,
long as
yeah,
there's
simply
some
if it's,
periodicity.
yeah, just a second. So simply if it's say Poissonian distribution from which observe data there, if you do the time series prediction, do you get it back?
I think, yeah, I think I've seen using Poisson distributions work in time series, but I can't really tell now. We can take this offline. I need some time to do some research about this because I can't really tell you right now.
Yeah, much of the
Thank you. And we have one more question.
Hi, Petal, this is Gopal. I just have a small query that imagine that we have a data which is progressive, continuously increasing. That we are working on a
Mhm.
product where the data is continuously increasing. So, like as far as we know that LSTM is a version from RNN, it is derived from RNN,
Mhm.
and recent update of this LSTM has helped us like in the deep belief system DBSH hypothesis. So those things have increased accuracy by some amount. But like what do you prefer? Like should I opt for KNN or should I opt for LSTM? Because the data is progressive. And you know that in LSTM it is recursive function, it is running, and too much of usage of CPU will increase. And we are
Yeah.
doing it on AWS, and you understand the compute
Mhm.
engines, how costly it is becoming. So
Mhm.
this is what our actual problem is. So what
Yeah,
would you
no,
suggest? Yeah.
I understand. Mm, Again, there's no simple answer. LSTM provides very accurate results in the first few predictions, depending on how many data points in the future are you trying to predict. How important is the error across the whole prediction period? Mm, I know there's a trade-off. LSTM usually provides good results, but what is the cost? Yeah, computation power, as you say, training takes very long. And it's a trade-off, but I always defend the traditional methods. Sometimes people just like to try the latest whatever trends are ongoing, but is it worth? Is it only marginally better compared to other methods? Is it worth the computation time and training time and so on? I don't have a simple answer. It depends on how important is getting the absolute best possible prediction compared to how much effort and time it means.
Yeah, thank you. So the tolerance in LSTM will be lesser, and here the tolerance will be more because the data could be fluctuating in KNN more and more. I'll be able to see the gaps. Here it will be mapped off. So that's the only trade-off that I'm looking for. We'll have a detailed discussion when I'm be coming here.
Yeah, anytime. Yeah.
Thank you. I see there are more questions on YouTube from Rahul Ashok, but due to time constraints, I think we can connect offline. Vital is our in-house data scientist, so please feel free to reach him on that note, thank you, Vital, for taking us on this mathematical journey of data forecasting and introducing us to the normal and deep AI/ML models. Thank you. Thank you all for your time today.
Yeah, thank you. Thank you. Have a nice day.
Please.
Thanks, Vital.